The problem situation states that a family-owned business dedicated to the production of ethyl acetate wants to optimize its production and increase their profits. They suggest removing water based on the fact that the chemical equation for the production of ethyl acetate is reversible. This is as follows. Ethyl acetate is a compound that derives from acetic acid and ethanol. It is very versatile and it plays a crucial role in the industrial laboratory. For instance, it is very used in the production of paints, coatings, adhesives, and nail polish removers due to its fast evaporation and low toxicity. It can be added to food and perfumes for its sweet and fruity aroma, and additionally, it is a key component in inks, plastics, and synthetic leather productions. Furthermore, optimizing the production of ethyl acetate is beneficial not only for the company, but also for the chemical process in general, since it is a sustainable solvent and it's a great alternative for fossil fuels. According to the U.S. Environmental Protection Agency, green chemistry is the design of chemical products and processes that reduce the generation of hazardous substances. It focuses on preventing pollution at a molecular level and applies innovative scientific solutions to lessen the negative impacts of chemical productions.
According to Le Chatelier's principle, if products are removed, then products will be formed. Thus, if we remove water, H2O, then the production of ethyl acetate will increase. This happens because for Kc to remain constant, if there is a decrease in the concentration of the products, then the reactants will create products to decrease their concentration and increase the concentration of the products for Kc to remain constant.
So the next question asks us if it is possible to create more ethyl acetate by other means, and the answer is yes, by modifying the temperature. As we saw in class, we are able to relate the Frey-Gibbs energy coefficient with the temperature and the chemical equilibrium constant of the reaction, meaning that if we know one of those or we modify one of those variables, we will have an effect on the reaction or in the chemical reaction. In this case, to know how the reaction will act, we need the enthalpy or the delta H, which gives us gives us the information regarding the nature of the reaction. In this case, whether if it is an endothermic or exothermic, and the production of ethyl acetate is an endothermic reaction, given this chart that was taken out from internet, and this means that we will have heat, or we can write heat as part of our reactants. So as we add heat to the reaction, we will have more energy in the reactants part, meaning that the products need to compensate this difference of energy by making more products. So therefore, by adding temperature and giving energy to the reaction, there will be a higher production of as ethyl acetate or an H2O. So yeah. So the last reaction was the enthalpy of the ethyl acetate formation based on the gas state of matter. However, we usually use the liquid form to form ethyl acetate. Therefore, we need to consider the next enthalpy coefficients to calculate the final enthalpy of the reaction. Based on the enthalpy coefficient, we know that this is a exothermic reaction because we have a negative coefficient, meaning that if we have heat, that would be in the product's side. So if we increase the heat, then we will create more reactants. So we need to do the opposite here. We need to reduce the temperature from the reaction in order to reactants compensate this loss of energy or this loss of temperature, so we are producing more products. So yeah, the reaction in liquid is the opposite from the gas state of matter.
So the amounts that we need for ethanol and acetic acid to produce ethyl acetates won't be equal to one another. And although we have the same number of moles of ethanol that react with acetic acid to produce ethyl acetate, and we can see this in the reaction as 1 mole of ethanol reacts with 1 mole of acetic acid to create 1 mole of ethyl acetate, we would still not have the same masses. And this is due to the use of the molar mass to make the relationship between all the substances. And for each substance, there will be a different molar mass. Then, if we assume that 1 ton of ethyl acetate is produced, we would need 0.52 tons of ethanol and 0.68 tons of acetic acid. And this was calculated first by converting the tons of ethyl acetate into moles of ethyl acetate using its molar mass, which is 88 grams per mole. Having this value, we can make the relationship with the stoichiometric coefficients in the reaction to get the moles of ethanol and acetic acid. Then we use our molar masses, which are 46 grams for ethanol and 60 grams for acetic acid, to calculate the grams. Then we converted the grams into tons, and this would result in the values that we mentioned previously. Now, it is important to mention that there is no limiting reagent, as there are one-on-one ratios. All the tons of ethanol that we just calculated and would react with the acetic acid, so all of these tons will be used to create 1 ton of ethyl acetate.
Hello, my name is Miranda Romero, and today we're going to answer the question: if the company has 500 liters of ethanol and 500 liters of acetic acid in inventory, what is maximum amount of ethyl acetate that could be produced? Okay, so first of all, we need to take a look to our reaction, which in our case is this one, and we need to ask ourselves, is it balanced, is it not balanced? Because if it is not balanced, we need to balance it first. That would be our first step. But in our case, it is already balanced, as we can see, because in the left side, in the reactants, we have 4 C's, 10 H's, and 3 O's. And in our right side, in our products, we also have the same amount. So it is already balanced, and we can skip that step. So in our case, our first step would be converting the volumes to moles. First of all, we have the volume of ethanol and acetic acid, which is 500 liters, and we have the density of both of them. So we know that the mass is equal to the volume times the density, and we can get the mass of both of them with this method. And after that, we can get the molar mass with the periodic table, and with the mass that we got in the first step, we can divide it times the molar mass that we got with the periodic table, and we can get, with this technique, the moles of both of them. Why we need the moles of both of them? Because we need to know which one is the limiting reactant. In this case, we can see that the smaller number is the ethanol's number, so we can see that the ethanol is the limiting reactant. And in our previous equation, or reaction, sorry, in our previous reaction, we can see that as it is already balanced, the stoichiometry is 1-to-1, so we don't need to change it, and we can, we can leave it like that. So yeah, we can use that moles of ethanol in the step 2, because that's our limiting reactant. Our step 3 will be to calculate the ethyl acetate produced. So as it is a 1-1 because of the stoichiometry reaction, it will be the same amount of moles that we got from the ethanol. And after that, we can get the molar mass of the ethyl acetate with our periodic table as well, and we can multiply it times the moles we got from the ethanol so we can get the mass. After that, we also know the density, and we can get the volume by dividing the density of the ethyl acetate and the mass. We divide the mass over the density, so we can get the volume that we need to answer our question. So we got that we have maximum of 836.8 liters of ethyl acetate. That would be our answer. Thank you.
But how do we know how fast the production of ethyl acetate is happening? To answer that question, we need to use chemical kinetics. Chemical kinetics, what would give us is a constant that describes the rate of change of the concentration over time. To do so, we need to take a small sample of the reaction at the conditions that we want, temperature, pressure, etc. Afterwards, we need to obtain the data of the concentration during that time. Given the data, then we plug the latter into the Excel or into MATLAB, and we try to fit the data to a linear equation based on the equations given regarding the order of the reactions. When we find a linear equation, then we find the order of the reaction. By knowing the order of the reaction, then we know how to calculate K. And by calculating K, we would know how fast the ethyl acetate concentration is increasing or how fast we are producing ethyl acetate.
Is there any way that the process of ethyl acetate production can be sped up? Well, yes. As a matter of fact, there are many factors that can affect the production of ethyl acetate or ethyl ethanoate, which is the systematic UPEC name for ethyl acetate. However, for simplification of the name, we'll use ethyl acetate. Now, to speed up the process, we have to look into temperature, pressure, catalyst, and the concentration of the reactants. All these 4 factors can speed up the production of ethyl acetate. Temperature can definitely speed it up. However, it also increases the risk of a more dangerous reaction. Aside from temperature, if you increase the pressure, it has the same effect as the one in temperature, increasing the speed, but also the dangers. But if you increase the concentration of the reactants, you will get a high rate of reaction. In the other side, if you add the right catalyst, you will also increase the rate of the reaction by lowering the activation energy. So, increasing the concentration of the reactants and adding the right catalyst might be a safer option than increasing the temperature or increasing the pressure. Now, is there an example of a chemical process that can be optimized in a similar way to this case of the production of ethyl acetate? Well, yes, there is another example called the Haber process in the production of ammonia. To produce 2 moles of ammonia, you need 1 mole of N2 and 3 moles of H2. In this reaction, if you decrease the temperature, it may favor the production of ammonia. However, it makes the process slower, meaning they might have to increase the temperature to an intermediate value. If you increase the pressure, according to Le Chatelier's principle, it favors the production of ammonia. As a catalyst, to increase the rate of the reaction, we must add potassium hydroxide as a promoter, which will increase the efficiency. Increasing the concentration of the reactants would also produce more ammonia, and at a faster rate. Both the production of ethyl acetate and ammonia are sped up by these 4 factors.
The information that can promote that this is a green product is that it is renewable and bio-based sourcing. It has low carbon footprint, low toxicity. It's human safe, generally not extremely toxic. Its rapid biodegradability is a great plus factor, as well as it has low air pollution.